Check. All right, good evening. How are you guys doing today?
Doing pretty good. Thanks for asking. How are you?
I'm all right. So let's go ahead and thank you for being here because I don't like talking to myself. Let's go ahead and get started. Which problem shall we look at first?
Number 1.
You want to go ahead and just walk through them? Sure. I didn't know if there was any particular one that was, you were going.
I couldn't find the exam 1 in the classroom. And the link didn't work.
Okay, so I don't know when you checked it. I'll double check it after we're done here. I believe that I had it hidden when I first sent out the email, because I was still working on it. And actually it should be hidden because I realized I need to update the equation sheets wrong. Or it's not wrong, it's just there's some equations that you need, but I'll make a note that I need to check D2L. All right. Okay. So here is our friend, the stress strain curve. You've seen this before. By the way, what is this type of material that typically gives us this look?
Steel, right? Mild.
Right, it's mild steel. Excellent. So we have some points here, and let's talk about what's going on at the points. So point A, helps if you're a pen. Point A here, right? That is Young's modulus. So that is our elastic region. All right. Point B, right? Any guesses what's going on at point B?
Would that be the yield point?
Yep. So that's the yield stress. And we did some problems where then we would label that sigma sub y. What is then going on from, well, what starts at C and basically ends at E? So our C, D, and E, what's going on in that area?
Is that the plastic deformation?
Well, that's the strain hardening.
Okay.
E is important, right? E is then our ultimate strength. All right, and finally over here at F, F is our fracture point. So F is where it is going to break. Amelia, does that answer your question on that one?
Yeah, thank you.
No problem. Okay. So next I ask about the difference between the stress strain curves for mild steel and for concrete. So Tyler just properly identified the last one we had, which is then for our mild steel. And the key is the mild steel has this little bump here before it fractures. So this would be my mild steel. All right, concrete. Can you get strain hardening with concrete?
No.
No, it's a very brittle material. So it's basically, it's going to come and then it's just going to break. The next thing on your thing is probably about word. On is more vocab, just to make sure you understand the terms. And so I'm not going to go over the individual terms, but let's go ahead and instead look at this particular problem. All right, so we have a circular aluminum tube, and we're given the length of our tube is 420 millimeters, and it is loaded in compression by a forces P. All right, now the hollow segment of length L over 3 has an inside outside diameter of 60 millimeters and 35 millimeters, and then we have a solid segment. All right, and that is a diameter of 60 millimeters. And we have a strain gauge placed in the outside of the hollow segment. And we want to measure, here we go, normal strains. Okay, so we're given actually the normal strain that is that's measured, and it's given to us as epsilon sub h because that's hollow, and it wants to know what is then the strain on the solid part. Okay, so what do we know? I don't have my list of equations, but we do know that the strain on the solid part times the area on the solid part, that is then going to have to equal the strain on the hollow part and the area on the hollow part. Now, our A's are going to be more than a little different. So that means we're solving for our strain on the solid part. So we're going to end up then with our area of the hollow over area of the solid, strain of the hollow. Okay, so in doing this, the area of the solid, that's pretty straightforward, right? And so that's going to be pi r squared, or they give us diameter, d over 2 squared, and the diameter of that solid part is 60 millimeters. And the answer I have is not in millimeters, it's in meters, but 2.837 times 10 to the negative third meters squared.
Can I
Ellie.
ask how you got the, like, where the strain times area, setting them equal to, um, how you came up with that equality?
Sure. So if you think about it, P is going to be the same on both ends, right? And so the strain is going to be, you look at it this way, the strain throughout this, if I measure the strain here or here or here, because of where that force is, that doesn't matter where I measure it, it's going to be the same, but we have a problem with the area. Let me grab our equation sheet. So we can grab the equation that I used to do that. Someone say something in the chat. No. So what do we know? We know sigma equals P over L, right? Which we're going to have to use in a minute. What else do we know? We know our epsilon equals then delta over L. All right. So if we look at this, we can also then rewrite, well, we can rewrite this then. Our sigma also equals epsilon times R E. Okay. So we're going to have what? We've got the P is going to be consistent throughout here. The L's are going to change. And then the areas are also, those are going to have to change. But no matter where we measure it, it's going to end up having to be then a ratio of the hollow section to the, because if this was all one piece, right, then the epsilon would just equal each other. But we have to put in that factor of dealing with the area. Does that make any sense?
Yeah, I mean, I was just a little confused because with the equation sheet, I was trying to figure out, because on the equation sheet, it just said stress and force, like stress equals force over length. And I couldn't rationalize doing the strain times area, setting those equal to each other.
Well, actually, I think I wrote this first one down wrong, didn't I? Didn't I? So this is sigma equals P over A, right? Okay, so what does this tell us? We have two areas, all right, but our stress in the two areas have to equal each other. So then we're going to have P, which is the same over A1. That's then going to have to P, which is the same over A2. All right, and as I mentioned, the P's here are the same. The other way, we also have the fact that the epsilon E, so I guess, but the strain has to be, do you agree, Tyler, the strain has to be consistent across the bar?
Yeah. Um, it's just like a little uncomfortable wrapping my head around it, but I mean, it makes sense.
Okay. All right. So now we need to find the area of the hollow section, which is going to be a little more challenging because that's then going to be R of the outside squared minus R of the inside squared. Okay, so that then is the outside is going to be the, so that's going to be pi. R of our outside is 65, 60, and then we have 35. So that's going to be 60 over 2 squared minus 35 over 2 squared. Okay. And so that's going to give us a 1.865 times 10 to the negative 3 meters squared. All right. So if we now want to figure out what the epsilon of the solid is, that's then going to be my hollow area over my solid area. And then we're going to multiply all of that by the given epsilon, which has a unit issue, I think. No, 470 times 10 to the negative 6. It's okay. All right. So we end up then with 3.101 times 10 to the negative 4th. So that's the first part of the problem. Part B is what's the overall shortening of the bar? Okay, so then we're going to want to use this delta equation here because we found the strain. So part B, right, we know delta equals then the strain divided by L. So wait, I think I just wrote that backwards, didn't I? Yeah, it's delta divided by L. Okay, our total, so our delta is then going to be epsilon times L. Our delta total is we're going to have to add up the delta of the two segments. So we have the delta of the hollow part plus delta of the solid. All right, and so that's then going to be epsilon of the hollow. Now we're given the total length, but we're told the hollow part is then L over 3. All right, and then we're going to add that to epsilon of the solid, which is 2L over 3. All right, so our epsilon of the hollow part is 470 times 10 to the negative 6. We're going to have to turn that L into meters. The L was given to us, so that's going to be what, 420 times 10 to the, oh, your author left it in terms of millimeters. Okay. We'll leave it in terms of millimeters. 420 divided by 3 plus, and then the other one we got was 3.101, 10 to the negative 4, 2 times 420 divided by 3. All right. And you plug that in a calculator, and I'm thinking you should get something about 0.1526 millimeters. Did that part make sense? Are we doing okay? Give me a 1 in the chat and let me know you're there. All right. Part C says if the compressive stress in the bar cannot exceed 48 megapascals, what is the maximum permissible value of the load P? Okay, so if we look at this, and you probably honestly could guess where this is going. For part C, we basically have 2 sections we have to worry about, and that is P max for the hollow section. So that's then going to be sigma sub A. That is, they gave that to us, didn't they? Yeah. So that's our compressive stress. All right. And then that's then going to be area of our hollow piece. All right. And so then if we put in P max of our solid, that's also then going to be sigma sub A, and then we'll have H of the solid piece. All right, so our area of our hollow piece ended up being 1.865. Right, times 10 to the negative 3. And we're then going to multiply that by the 89.5 kilonewtons. And somehow the author got, trying to think about this. Right, that was given to us 89.5. Oh, I'm sorry, 48 megapascals. Okay, that's what's going wrong. All right. So this is the answer. So we then have 48 megapascals. All right, and when we multiply those together, we're going to get 89.5 kilonewtons. We now look at P max for the solid part of the bar. By the way, what does your gut say? Would the solid part of the bar be can take more force or less force than the hollow part? Yeah, more force. So we multiply this by the 48 megapascals. All right, and then that's going to end up being 135.7 kilonewtons. All right, so as Amelia said, the solid part's going to need more force. Okay, so this is going to be then our max because it's the smaller one. All right, so Ellie's joined us and Kate has joined us. Which one should we do next? Anyone have any thoughts?
I think maybe number 8 or 7 would be good for me.
Okay, so I put 2 number 8s in. Do you want this number 8 or this number 8?
The second one, the one you're on right now.
Okay. Okay. So we have rubber pads, thickness was T equals 9 millimeters, and it's bonded to steel plates. And we're given then the length of the pads. So we have rubber pads. All right, and we know T equals 9, so my thickness is 9. My length is 160, and my width is then going to be 80. All right. And then we're given 2 other pieces of information. The average shear strain, gamma, all right, fine, well, that's what we're finding. If the force, so we're told our force here is going to be 16 kilonewtons, and we're given G, right? And that's because, why are we given G instead of E for this problem? What's the difference?
Because it's shear.
Right, we're dealing with shear. Okay, so we're dealing with our shear stress, right? So that's then going to be our force divided by our area. Now, the force on this one is, you're actually looking at the force that the rubber pad is seeing. And because the rubber pad is seeing those 2 surfaces, and I noticed this was a problem on the quiz, this is going to end up being 16 divided by 2. All right, and then that's going to be over our area, which is then going to be 80 times 160. So that ends up being 625 kilopascals. Okay. The reason we want that is because our strain is then going to be our stress, and I think I mentioned that you guys are missing some equations off your equation sheet, and I'll revise your equation sheet tonight over G. And I'm thinking these were maybe missing. Maybe these were okay. Maybe it was the prismatic bar ones that were missing. So this ends up being then 625 kilopascals over 1250 kilopascals. All right. And that's then going to equal 0.50. And that is then unitless. All right. This causes a horizontal displacement. And I believe you saw this drawing in class. All right. This here, this is then my gamma average. So that's going to be my strain. Okay, so, and we want to know the horizontal displacement. So this is my delta, and then this here is then the thickness. So tangent of gamma is then going to be delta divided by my thickness, or delta equals thickness tangent of gamma. All right, and so that's going to end up then being 9 and tangent of 0.5, which is unitless. So since it's unitless, you want your calculator in radians, 4.92 millimeters. Kate corrected me on something. Something was gigapascals. Oh, the G is in gigapascals. God. Okay, so I think, and the drawing showed it to you, but I noticed this was a problem. You know, this is, we were talking about this relative to bearings, but it works the same way because we have multiple forces going on. So Ellie, I have to ask, what is that creature? Is it a spider?
It's actually a rain frog.
Oh, okay. All right. Kind of creeping me out. Okay. So, which one did you also say 7? Did you mean this one or did you mean this one? Tyler,
The one you're on right now.
the one I'm on? Sure.
Yeah.
All right. Is everyone else okay with us spending some time with this one? All right. So we have two steel tubes are joined together at B by 4 pins, and we're given the diameter then of those pins. All right. As shown in the cross section. The outer diameter of the tube is 41. Then we're given DAB is 41, DBC is 28, and they give us the 2 wall thicknesses. So both of these are hollow. The yield stress in tension for the steel is 200 megapascals, and the ultimate stress in tension is 240 megapascals. All right, and then they tell us the corresponding yield and ultimate values for the pins. And then the bearing between the pins and the tubes, and we're given that as well. All right, now here is where sort of the I don't know, rubber meets the road, so to speak. Okay, we are given the safety factors for the pin, which is 3.5, right, and 4.5. So we want to figure out what is the allowable force, right? And our safety factors, let me go back and look. Okay, so we have a couple, if you look at your equation sheet, which if you arrived late, needs to be adjusted for the last, because of the last couple of problems. But we have the fact that our, so these are coming off the equation sheet. Sigma allowed is then the yield over N1, all right? And sigma allow is then going to be the ultimate, and we'll then call that N2, or the second safety factor. All right, we also have our shear. So tau allowed right is then going to be I don't think those equations are right now. I don't think we need tau allowed, because that is, oh no, we are, because we're going to have to do the shear. Okay, so part A wants to know the allowable tensile force that can occur. Okay, and so that means that we know sigma equals P over area. Right, and we are given some different values of stresses, right? And we're going to have some different areas that we need to work with. Okay, so we've got two tubes. Do we agree? Right, we'll call this tube 1, and we'll call this tube 2. And we want to figure out P allowed for the tubes. Then we're going to go back and we're going to figure out P allowed for the pins and the shear in the pins. So this would then be the tau expression. And then between the bearing, the pins and the tubes. And they want to know which is the controlling value of P. So as we saw in the last problem, the controlling value is always going to be the smallest value. All right, so let's go ahead and figure out what is going on with all of these numbers up here. Let's break it down. So we have a tube. All right, and the tube is, the first tube we have is, I was going to call it AB, but hang on. Oh, okay. So both tubes have the same. The difference is going to be then their diameter. All right, and so the tubes have sigma sub y is 200 megapascals. Sigma sub u, or the ultimate, is then going to be 340 megapascals. Okay, now we've got some different safety factors. All right, and so the safety factor for the steel part is then, I have in my notes that it's 3.5. Does that make sense? Yeah, okay. So we then have our safety factor of 3.5. All right, so what can we get? And I'm gonna need some numbers. Well, I was gonna say I was gonna need some numbers run. But we know we've got our sigmas. So our sigma sub y over our safety factor, right? That's then going to equal our P allowed over the area. All right, we're going to have to calculate this twice to see which one is, for lack of a better term, in control. Okay, because we always look for the smaller one. So we'll start with tube AB. All right, and so the area all right, let's just pull that pi over 4 out. So we're given a lot of information here, but I think this drawing is actually rather helpful. So we're going to have then the outside area minus, and then we're going to have the inside area. Well, we need the inside area, so that's going to be the outside area minus the thickness. Okay, so this is my outer diameter minus my inner diameter, but we're not given that inner diameter, so we have to calculate it. The reason we're multiplying here by 2 on the thickness is because we're dealing with diameter, not by radius. So if you look, you've got your outer diameter here, and then you've got an inner diameter, or the inner diameter is then going to be affected here and here. All right, so if we put these numbers in, so it's going to be 41 squared minus, and then we're going to have 41 minus 2 times, and I believe they're different, correct? TAB is 41, 6.5. Okay, 2 times 6.5 squared. All right, and that's going to then ultimately give us an area of 418.502 millimeters. So our pressure or force that this can handle, and this is tube AB, right? That's going to be our sigma sub y divided by our safety factor times our area. All right, and so my area ended up being 418. So this is going to be 200, and it's in megapascals, divided by the safety factor we're given for the yield strength, which is then going to be 3.5 times the 418.502 millimeters squared. But we got the megapascals. All right, so when you put that in a calculator, I do believe you end up with 8743.9 newtons. Okay, so that's this tube's yield. Now let's look at this tube's ultimate. So that's going to be sigma u over n times the area. All right, which our ultimate was 240. So that's going to be 240 megapascals over 3.5. And then this is going to be 418.502 millimeters squared. And I'm thinking, well, it looks like this comes out to be 11,000 newtons.
Excuse me?
Yeah.
Isn't the 240 340? Oh, I think I wrote it wrong.
Oh, okay. I'm seeing 200 here and then 240 there.
Okay, okay.
Okay, so now we need to look at what's happening for this tube number 2 or the BC tube. All right, so we'll look now at tube BC. All right, so we are then going to have to figure out the area. You know, it's going to be the same series of equations. P is going to be then sigma y over the safety factor. Oh, I wrote the wrong safety factor, didn't I? Hang on. Because 4.5 is for the ultimate. So this is not 3.5. This is 4.5. All right, times the area of BC. And then this is going to be, I'll call it n sub y. And then P is going to be U over n sub U area of BC. So to find the area of BC, this is that second tube, pi over 4. We're then going to have D of BC, and that is then going to be squared. So that's my outside minus my inside. D of BC minus 2T of BC squared. Okay, so that's going to be pi over 4. Sorry, I got distracted. So that's going to be, let's see, this one, the second one is, one was 41 and the other one is 28. And its thickness is 7.5. Okay, so this one comes out to be then 153.02. At this point, we actually don't need to go any further because that is going to give us a bigger P, right? Because this is a larger area. And in order for us to figure out what's allowed, we need to look at which one is the smallest. So the smallest on this one is going to then be this here. So that was part A. Part B, we're now going to go after the pins for part B. Well, okay, even with 682, that's still bigger than the 418 number, right? So you're going to end up with a bigger force there. Let's make sure we talk through part B, right? Because now we're going to look at shear in the pins. So we're now dealing with our tau. So our tau is then, it's going to be the same sigma y over our safety factor. And then we're going to have tau of u is then going to be sigma u over this particular safety factor. Okay, so what ends up happening is we'll end up with P if we is then going to be tau sub y, and I believe we were given that information, weren't we? That's going to be tau sub y over the yield safety factor times the area. But how many pins did it tell us that we had? 80. I thought it said 4. I'm so freaking lost. Oh, it is 4. Okay. So, oh, okay. All right. So this has to be multiplied then by 4. We're given our, and the area is actually easier to calculate. And that is the fact that the area of the pin is then going to be pi over 4, the diameter of the pin squared. And the diameter of the pin is 11. So that ends up being 95 millimeters squared. All right. So our tau for this was given to us, tau y, oh, that's the 80. All right, 80 then over 3.5, right, times 4 times that 95 number. And that is going to end up being, well, we'll end up with 2 numbers. One is going to be 86, 88. So that's from the yield stress. And that's in newtons. And then we're going to do the same thing with the ultimate shear. And that one ends up being 11,826.3. So this is the smaller one. Okay, this is also smaller, I believe. That's back here. Yeah, that was 87. This one's ends up being 86. So for part C, once again, you want to look for the smaller control, and it's going to have to be that this the yield strength of the bearings is what's going to control it. All right, what should we do next? By the way, it looks like I got carried away on your review. Your exam questions are not nearly this hard, so do not freak out.
Dr. Minky,
Yeah,
so on your screen right now where you have the force equals tau sub y over n sub y, and then
Yeah.
you have force equals tau sub u over n sub u.
yeah.
Is it, what would you call what is the tau sub y again? Is that the yield?
Yeah, that's going to be, so if we go back, to here. So the shear and what have you, that's happening then at B, and then the ultimate would then be over here at E.
Okay, so is it not the case? I guess it's probably dependent on material, but the way I see it, like I'm having trouble figuring out whether or not wouldn't the ultimate always be higher than the yield? Or is it the
The
same?
yield is always going to be lower than the yield. So you certainly could use that as rationale as you're working through this, saying, I'm only going to calculate based on the yield because the yield is always going to be lower than the ultimate. So the controlling factor is always going to be from the yield. Yes, you are
Okay.
100% correct.
Okay, cool. I was curious why we were doing both of those. But yeah, thank you.
Yeah. So, we do have a couple left. As I said, I got a little carried away, but I don't think the one on your exam isn't like this, but I want to talk about this one here. And this brings in, Tyler was asking in class about the N business. All right, and N is just P in the normal direction. And the reason I want to talk about this one is because we have a slight issue going on. As I said, I got carried away when I put these together. So delta, we know delta is PL over EA. And there are, for lack of a better term, there are some assumptions that we make for this particular equation. P is the force and L is the length, which is fine. And E is the static quantity or the elasticity of modulus, but it's the A here. So if I have a bar, and it doesn't matter if it's solid or hollow, the A is basically going to be the same throughout the bar. That is not the case for this, because you will notice that this is not a bar, this is a cone, kind of. But we really can't use the area of a cone either. And so what we're going to have to do with this is we're basically, and this is, Tyler brought this up in class, right? We're going to need then to, this was given to you in the book, but it's 0 to L. Instead of the P, they put it in as N sub X. N sub X would mean that the force is varying with the length, dx over E AX. But what's happening on this one is we only have one P. And so if we look at this, the E is going to be constant. The N is basically P. All right. So P is going to come out. E can come out, and that ends up with 0 to L then of dx over AX. So that's how they get the crazy equation that they're doing with this one. The one that you're doing, because you've got a different I've got A as a function of X, and the thing is that L goes, I have this 0 to L, but what's changing is the diameter. So A is a function of X. We know area is then going to be pi over 4 d squared. The d is what's going to be changing. It's going to go from B2 to B1, and then it's going to go from B1 to B2. So that makes this one, I think I pulled this out of your homework, but it makes it a little unusual because of that. And I wanted to make sure you had a chance. Have a chance to do that. So it is 7:30. A couple of problems we didn't get to. So I will go ahead and make this a group work assignment and let you guys go through the rest of them. I'll make myself another note. I need to check D2L to make sure that you can see the exam. And then the other is to check group work. Is open a group work for this, for the last couple of problems. Once again, if you can master these problems, the exam for you is going to be a joke. The exam problems are not nearly as challenging as these problems. I got a little carried away. All right. Actually, I pulled it from a previous year, and my guess there was a student in that class that annoyed the heck out of me, and I'm guessing that's why I did it that way. All right. I was taking revenge. But I would never do that on an exam. And you guys are all wonderful, so that won't happen to you folks. All right, so thank you so much for joining me this evening. I will get this uploaded for you, as well as the video. There is no lecture on Thursday. If you are virtual, nothing is happening in class on Thursday. All right. And I'll send out an email, and I'll send out the equation sheet. I believe there are 7, no, I know there are 7 problems on the exam. All right. You will have the entire class period to be able to complete this. All right. All right, you guys have a good evening. Stay safe out there. It's a little wet. You're welcome. And I'll see some of you on Tuesday, and the rest of you, I will either see you Thursday or I'll see you 2 weeks from Thursday. And have a great evening. Or I'll see you tomorrow.